Welcome back to the Science Pillow, where the universe always has something new to whisper into the darkness. Before we begin tonight's journey, if you find that this channel helps you drift off or simply unwind at the end of a long day, consider hitting that subscribe button and leaving a like. It takes only a moment, and it helps this little corner of the universe reach more people who might need exactly what you need right now. A calm voice, a fascinating story, and permission to let the day go. And if you're watching for the first time, welcome. You found a place where we take the biggest questions humanity has ever asked and lay them out gently, like a blanket, for you to rest underneath. Tonight, we are heading to the absolute edge of our solar system, not the comfortable edge, where Pluto drifts in its familiar frozen loop. We are going somewhere far colder, far darker, and far more mysterious than that, to a place where the sun is little more than the brightest star in an otherwise uniform sky, and where a ghostly world may or may not be circling us, unseen. In one of the longest orbits ever proposed for a planet, a candidate for Planet 9 was recently found hiding in decades-old data. Astronomers were cautiously, and then, almost immediately, someone pointed out that something was very, very off. That's where our story begins. Let the weight of the day settle from your shoulders. Take a slow breath and join me out here on the frozen frontier. Part 1. The Frozen Frontier. Setting the stage. Close your eyes for a moment, if you'd like, and imagine that you are no longer on Earth. You have drifted outward through the solar system, past the warm, rust-colored deserts of Mars, past the swirling amber storms of Jupiter, past the serene rings of Saturn, past the strange tilted world of Uranus. You pass Neptune, that deep blue sphere of turbulent gas, and as you do, you cross an invisible threshold. You leave the realm of the known planets behind. And what you find out here is not emptiness. It is something stranger and quieter and more ancient than that. Out here, beyond Neptune's orbit, the solar system becomes a different kind of place entirely. Neptune sits about 30 astronomical units from the Sun, 30 times the distance from Earth to the Sun, which is about 93 million miles. That means Neptune orbits about 2.79 billion miles from the center of our solar system. It takes that planet 165 Earth years to complete a single orbit, and yet, by the standards of what lies beyond, Neptune is practically our neighbor. In the region just past Neptune lies the Kuiper Belt, a broad, flattened disk of icy bodies that extends from about 30 to 50 astronomical units from the Sun. Think of it as a second asteroid belt, but composed primarily of ice and frozen compounds rather than rock. Pluto lives here, along with thousands of other worlds, many of them unnamed and barely studied. Objects in the Kuiper Belt are the frozen leftovers of the solar system's formation, preserved in the deep cold like fossils in amber, holding clues about the conditions of the early solar neighborhood 4.6 billion years ago. The sunlight that reaches the Kuiper Belt is a faint, thin thing, far too weak to warm any surface there even slightly. Temperatures hover around -220 degrees Celsius or -364 degrees Fahrenheit. To put that distance in a different kind of perspective, if you could somehow travel at the speed of light, which is approximately 186,000 miles per second, you could circle the Earth more than 7 times in one single second. And yet, even at that incomprehensible velocity, it would take light from the Sun about 4.5 hours to reach Neptune, and then another hour or more to cross the Kuiper Belt entirely. The distances we are talking about here are not gaps in the way that the space between cities is a gap. They are vast, cold, essentially empty expanses of space in which occasional icy objects drift in enormous, nearly circular paths around a star that looks, from where they float, like the brightest star in a sky full of stars. The Kuiper Belt is not uniform. It has structure, texture, architecture. Objects within it fall into different, dynamical categories based on their orbital relationships with Neptune. Some are in stable resonances with that giant planet, orbiting the Sun in simple integer ratios relative to Neptune's orbital period, much the way Jupiter's large moons maintain their orbital harmony with each other. Pluto itself is in what's called a 3-2 resonance with Neptune, completing exactly 2 orbits around the Sun for every 3 orbits Neptune completes. This resonance protects Pluto from ever getting close enough to Neptune for a gravitational catastrophe, even though their orbits technically cross. Other Kuiper Belt objects are not so lucky, and their orbits are gradually modified by gravitational nudges from Neptune over hundreds of millions of years, sometimes being scattered into the inner solar system as comets, sometimes being flung outward to greater distances, sometimes just drifting quietly in stable configurations for as long as the solar system exists. Beyond the Kuiper Belt, the solar system continues to sprawl in ways that are difficult to intuitively grasp. The entire Kuiper Belt itself is already so distant that the Sun, from any point within it, would look like an extremely bright star rather than the overwhelming disk of fire we see from Earth. You would still be able to read by its light, just barely, and you would feel no warmth from it at all. At about 50 astronomical units, the Kuiper Belt effectively ends, though the reason for this abrupt edge is not fully understood. This termination is one of the smaller mysteries of our outer solar system, waiting patiently for an explanation. Beyond this edge, objects become increasingly sparse. We enter a region sometimes called the scattered disk, populated by objects that were gravitationally flung to great distances during the chaotic early history of the solar system, when the giant planets were migrating and stirring up everything around them. And further still, much, much further, lies the Oort cloud, a vast spherical shell of icy bodies that encompasses the entire solar system like a bubble. The Oort cloud stretches from roughly 2,000 astronomical units all the way out to perhaps 100,000 astronomical units, which is nearly halfway to the nearest star. This is where most long-period comets originate, nudged out of their ancient orbits by the gravitational influence of passing stars or the gentle cyclical tugging of the galaxy itself. No spacecraft has ever reached the Oort cloud. No telescope has ever directly imaged it. We know it exists mostly through the comets it sends our way and through theoretical models of how the solar system must have formed. In between the outer edge of the Kuiper Belt and the inner edge of the Oort cloud lies what some astronomers call the inner Oort cloud, or the extended scattered disk, a transitional, poorly understood region where a handful of strange, isolated objects wander in orbits so large that they take thousands of years to complete a single revolution around the Sun. This is the domain we're stepping into tonight. This is the place where one of the most extraordinary and frustrating detective stories in the history of modern astronomy is unfolding. Because somewhere out there, in the darkness beyond Neptune, something might be waiting to be found. Something with enough mass to reshape the orbits of dozens of smaller worlds, leaving its gravitational fingerprints all across the far reaches of the solar system. Or it might not be. And that uncertainty is at the heart of tonight's story. To understand why scientists are even looking for a new planet out here and why the search has become so urgent and so contested in recent years, we need to go back in time. Not just a decade or two, but nearly 2 centuries, to a moment when mathematics revealed an invisible world and changed the way humanity thinks about what lies beyond the edge of what we can see. Part 2. A 200-year obsession. The hunt for Planet X. The story of searching for hidden worlds in the outer solar system begins in the early 19th century with a crisis in the orbit of Uranus. Uranus was discovered in 1781 by William Herschel, a German-born musician who had immigrated to England and taught himself astronomy with such devotion that he became one of the greatest observational astronomers in history. He was scanning the sky on the night of March 13, 1781, when he noticed an object that appeared distinctly different from a star. It showed a disk, not a point. He initially thought it might be a comet, but as other astronomers tracked its motion, it became clear that he had stumbled upon a new planet, the first in recorded history to be discovered by observation rather than known since antiquity. Uranus expanded the known solar system at a stroke. It roughly doubled the radius of the planetary system. And, for several decades, astronomers tracked its orbit with great care, working out its path and confirming the predictions of Newtonian gravity with satisfying precision. Until they couldn't. By the 1840s, something troubling had emerged. Uranus wasn't moving quite the way it should. Its actual position, measured night after night through careful telescopic work, kept drifting away from where the mathematics said it should be. The discrepancy was small, a matter of arcseconds, the angular equivalent of tiny fractions of a degree. But it was persistent and systematic, not the random scatter of measurement error. Something was pulling on Uranus, tugging it slightly off course in a way that the gravitational influence of the known planets couldn't explain. 2 mathematicians, working independently and not initially in communication with each other, came to the same conclusion. The discrepancy in Uranus's orbit could be explained by the presence of an undiscovered planet, orbiting even further from the Sun and exerting a subtle but measurable gravitational pull. Those 2 mathematicians were the Englishman John Couch Adams and the Frenchman Urbain Le Verrier. Both worked out the orbital mechanics and predicted where the unseen planet should be based on the gravitational effects it would need to produce. Le Verrier sent his predictions to the Berlin Observatory in September 1846, and on the very night that astronomer Johann Galle received Le Verrier's letter and pointed his telescope at the predicted location, he found Neptune. It was within 1 degree of where Le Verrier had said it would be. The discovery was immediately recognized as one of the greatest triumphs of mathematical physics, the first prediction and confirmation of a major world through pure mathematical reasoning. But triumph in science so often comes attached to a new puzzle. Almost immediately after Neptune's discovery, some astronomers began to notice, or thought they noticed, that even accounting for Neptune's gravity, small irregularities remained in the orbit of Uranus. And Neptune itself seemed to have minor anomalies of its own. The Neptune solved it story felt incomplete. Maybe there was yet another planet, lurking even further out, shepherding the ice giants in ways that hadn't yet been fully accounted for. This suspicion found its most passionate advocate in Percival Lowell, a Boston aristocrat and mathematician who devoted much of his life to the question. Lowell is better known today for his fervent and ultimately incorrect belief that Mars was crisscrossed by a network of artificial canals built by a dying civilization. But he was also a serious and mathematically rigorous astronomer who founded the Lowell Observatory in Flagstaff, Arizona in 1894, an institution that continues to operate and make important discoveries to this day. Beginning in 1906, Lowell set out to find what he called Planet X, a hypothetical world beyond Neptune, whose gravity would explain the residual orbital anomalies of Uranus. He hired a team of human calculators, people who performed arithmetic for a living, a job that carried the same title then that electronic computers carry today, and set them to work on the tedious, exacting mathematics of orbital mechanics. Over the course of a decade, Lowell and his team photographed wide swaths of the sky, comparing pairs of images taken weeks apart, looking for the telltale drift of a slowly moving planet against the fixed background of stars. They did not find what they were looking for, but they did accumulate an enormous archive of sky photographs that would prove historically important. Percival Lowell died in 1916, before he could realize his dream of discovering Planet X. But the search he began continued after his death. In 1929, a young astronomer named Clyde Tombaugh arrived at Lowell Observatory from his family's farm in Kansas. He was 22 years old, largely self-taught in astronomy, and brought on to continue the systematic search of the sky that Lowell had begun. Tombaugh was assigned to work with a new 13-inch telescope and a device called a blink comparator, which allowed him to rapidly alternate between two photographs of the same patch of sky taken at different times. Any object that had moved between the exposures would appear to jump back and forth, drawing the eye. On February 18, 1930, Tombaugh found something jumping. In images of the constellation Gemini, taken about 2 weeks apart, a tiny point of light had shifted. He had found a new world, one that was named Pluto, after the Roman god of the underworld, partly suggested by an 11-year-old English girl named Venetia Burney, and partly adopted because the first two letters honored Percival Lowell. The solar system had, it seemed, a 9th planet, but the celebrations were premature. Pluto turned out to be far too small to explain the orbital anomalies that had motivated the search in the first place. Its mass was eventually calculated to be only about 0.2% of Earth's mass, completely insufficient to have any measurable gravitational effect on Uranus or Neptune. Even stranger, when the Voyager 2 spacecraft flew past Neptune in 1989 and allowed scientists to calculate Neptune's mass with much greater precision, it turned out that the apparent anomalies in the orbital motions of both Uranus and Neptune essentially disappeared. They had been artifacts of slightly incorrect earlier estimates of Neptune's mass, not evidence of an undiscovered planet at all. This was a humbling revelation. The entire 70-year hunt for Planet X, the observation, the mathematics, the late nights at the telescope, the eye strain of the blink comparator, had been motivated by a systematic measurement error. Lowell and his successors had been chasing a ghost, a mathematical phantom, created by imprecise data rather than a real world. It served as a powerful reminder that in science, the evidence for a hypothesis is only as good as the quality of the observations underlying it. Seeing a pattern in the data does not always mean the pattern is real. The discovery of Pluto was later reinterpreted not as the discovery of a 9th planet, but as the first discovery of a new class of solar system objects, the trans-Neptunian objects. Beginning in the 90s, astronomers began finding more and more objects in the region beyond Neptune, first slowly, then in increasing numbers, as telescope technology improved and systematic surveys began. By the early 2000s, it was clear that Pluto was not a lonely anomaly, but the largest known member of a substantial population of icy bodies in the Kuiper Belt. And in 2006, the International Astronomical Union voted to formally reclassify Pluto as a dwarf planet, not because it had changed, but because our understanding of what it represented had finally caught up with the reality of the outer solar system. The hunt for Planet X appeared to be over. Its founding premise dissolved by better data. The solar system had 8 planets, the textbooks were updated, and the idea of a hidden giant world in the deep outer solar system seemed to belong to an earlier, less precise era of astronomy. And then, in 2003, everything changed again. Not with a prediction, but with a discovery. A single, deeply peculiar object found by the same astronomer who would help kill Pluto would eventually restart the search for a hidden world on far more solid scientific ground than anything Percival Lowell had imagined. Part 3. Sedna and the First Clues. On the night of November 14, 2003, astronomer Mike Brown and his colleagues at the Palomar Observatory in California were conducting a systematic search for distant objects in the outer solar system. Brown was the leader of a prolific Caltech team that was in the process of cataloging the Kuiper Belt in unprecedented detail. They were using a wide-field camera on the 48-inch Samuel Oschin Schmidt telescope to survey large swaths of sky, then carefully comparing the images to find anything that was moving, the telltale sign of an object within our solar system, as opposed to the infinitely more distant background stars. What Brown and his colleagues found on that November night was not what they expected. They found an object moving extremely slowly, far more slowly than anything they had typically seen in the Kuiper Belt. Slow motion, in this context, is an indicator of distance. Objects move more slowly across the sky the farther they are from the sun, because their orbital velocities are lower and because the same angular change corresponds to a much larger physical distance at greater range. The slowness of this new object's apparent motion suggested it was extraordinarily far away. Follow-up observations over the next weeks and months confirmed the suspicion and revealed something genuinely baffling. The object, later named Sedna after the Inuit goddess of the sea, thought to live at the bottom of the Arctic Ocean, was orbiting the sun on a highly elongated elliptical path. At its closest approach to the sun, which astronomers call perihelion, Sedna comes no closer than about 76 astronomical units, more than twice Neptune's distance. And at its farthest point, its aphelion, Sedna swings out to approximately 937 astronomical units, nearly 1,000 times Earth's distance from the sun. Its orbital period is estimated at around 11,400 years. Right now, in 2026, Sedna is slowly approaching its closest point to the sun, which it won't actually reach until around 2076. Mike Brown, who had developed a reputation for finding unusual objects in the outer solar system and for rigorously applying the definitions that led to Pluto's demotion, called Sedna the most scientifically interesting object he had ever found, not because of what it is, but because of where it is and what that implies. The problem with Sedna is that there is no good natural explanation for its orbit within the framework of the known solar system. Objects in the Kuiper Belt were scattered to their current positions by gravitational interactions with Neptune during the early chaotic period of solar system formation. But Sedna is far too distant to have been pushed there by Neptune. Its closest approach to the sun, at 76 astronomical units, keeps it well out of Neptune's gravitational reach. Neptune's influence fades dramatically beyond about 40 astronomical units. Sedna exists in a gravitational no-man's land, too far for Neptune to have placed it there, but too close to the Sun to have been affected by the galactic tidal forces that shape the Oort cloud. Something else must have put Sedna on its extreme orbit. Multiple explanations were proposed. Perhaps the Sun, in its youth, was surrounded by a cluster of sibling stars, and one of those passing stellar companions had gravitationally nudged Sedna out to its current position during a close encounter in the first few 100 million years of the solar system's life. Perhaps Sedna was captured from another planetary system during such a close passage. Or perhaps, and this was the idea that lingered most provocatively, there was an undiscovered planet massive enough to gravitationally deflect objects into these strange, isolated orbits. At the time, Brown and his colleagues considered the Planet X explanation, but thought the stellar flyby hypothesis was more likely. They continued their systematic survey of the outer solar system and moved on to other discoveries. Sedna was cataloged and filed away as a fascinating mystery, but it didn't immediately launch a revolution. The solar system harbored plenty of mysteries, and not all of them required new planets to explain them. But Sedna had planted a seed. It had proven that objects could exist in the outer solar system in configurations that didn't fit neatly into the standard model of how the solar system formed. And it had done something even more valuable than that. It had given astronomers a new target, a new parameter to search for. If Sedna's orbit had been shaped by an undiscovered, distant planet, there ought to be other objects in similar orbits, a family of stranded worlds, all sharing the gravitational fingerprint of whatever had perturbed them. Finding more objects like Sedna would help build a statistical case for or against a planetary perturber. In 2014, astronomers Chad Trujillo and Scott Shepard found another Sedna-like object, designated 2012 VP113, at a perihelion distance of about 80 astronomical units. It was another isolated inner Oort cloud object that couldn't have been put on its current orbit by Neptune alone. And in their paper announcing the discovery, Trujillo and Shepard noted something important. Both Sedna and 2012 VP113, along with several other distant Kuiper Belt objects, seem to share a common value for a particular orbital parameter called the argument of perihelion. This number describes the orientation of an object's closest approach to the Sun in three-dimensional space, and the fact that several distant objects were clustering around the same value suggested it might not be a coincidence. It was a subtle clue buried in the mathematics of orbital dynamics, but it caught the attention of two astronomers at Caltech who would turn it into an extraordinary hypothesis. Part 4. The 2016 Bombshell. Batygin and Brown. The year 2016 began quietly enough in planetary science. But on January 20th, Caltech astronomers Konstantin Batygin and Mike Brown published a paper in the Astronomical Journal that would rearrange the conversation about the outer solar system almost overnight. Brown is a veteran of the outer solar system. He is the same Mike Brown whose systematic surveys of the Kuiper Belt had led to the discovery of Eris, a body slightly smaller but more massive than Pluto, which forced the planetary definition crisis and ultimately led to Pluto's demotion. He genuinely didn't want to be the person who proposed another new planet. He had spent years explaining why there wasn't a Planet X, why the old Lowell-era anomalies were artifacts of bad data, why the idea of undiscovered giant worlds in the outer solar system was almost certainly wishful thinking. When he and Batygin started examining the orbital clustering that Trujillo and Shepard had noted, Brown's initial instinct was to find the most mundane explanation he could. Batygin brought a different kind of expertise. He was a dynamicist, a theorist who specialized in the mathematics of how gravitational systems evolve over long time scales. And when the two of them began running detailed simulations of the outer solar system, what they found was that the clustering of distant Kuiper belt objects was extraordinarily difficult to explain without an external perturber. They ran simulation after simulation, trying to account for the clustering through observational bias, through the gravitational effects of the known giant planets, through random chance. None of these alternatives worked well enough to be convincing. What did work spectacularly was adding a distant, massive, unseen planet on an elongated, inclined orbit to the simulation. When Batygin and Brown inserted a hypothetical planet with a mass of approximately 5 to 10 times Earth's mass, orbiting on an eccentric path with a semi-major axis of several hundred astronomical Greeks, the simulations produced the observed clustering of Kuiper belt objects naturally, as an expected consequence of the planet's long-range gravitational influence. The planet didn't need to be anywhere near these objects at any given time. Its influence, accumulated over billions of years, was enough to shepherd them into the orientations that were actually observed. The statistical case for the planet was striking. Batygin and Brown found that the probability of the orbital clustering occurring by random chance in the absence of any external perturber was about 0.007%, roughly 1 in 14,000. Subsequent analysis, carefully accounting for observational biases in how astronomers search for these objects and correcting for where they tend to point their telescopes, reduced the probability of chance clustering, but still left it at roughly 0.2%, or about 1 in 500. That's not certainty, but it represents the kind of statistical signal that makes scientists pay close attention. Their paper proposed a specific set of characteristics for the hypothetical planet, a mass of roughly 5 to 10 times that of Earth, placing it in a category astronomers call super-Earths, or mini-Neptunes, an orbital period between 10,000 and 20,000 years, and a semi-major axis that would put its average distance from the Sun somewhere between 400 and 800 astronomical units, with its closest approach potentially as near as 200 to 300 astronomical units, and its farthest point potentially exceeding 1,000 astronomical units. The predicted orbit was highly eccentric, elongated like a stretched ellipse, and inclined at an angle of roughly 15 to 25 degrees relative to the flat disk of the solar system. The planet they proposed would also explain several other puzzling features of the outer solar system that had previously resisted explanation. Objects in highly inclined and even retrograde orbits tilted so steeply that they circle the Sun in the opposite direction from everything else, were known to exist in the outer solar system, and they made no sense in the context of a smooth, well-behaved solar system. Batygin and Brown showed that Planet 9's gravity could, over billions of years, torque the orbits of distant Kuiper belt objects into these extreme configurations, creating the unusual population of high-inclination objects that surveys had been finding. The planet could also explain the curious, detached orbits of objects like Sedna, using its gravity to gradually pull perihelion distances outward, lifting objects away from Neptune's influence and into the isolated inner Oort cloud. The publication of the paper was, in the world of planetary science, Something like a thunderclap. It attracted immediate international media coverage, spawned dozens of follow-up studies, and launched an intense global search. Astronomers around the world began pointing their best telescopes at the regions of sky where Planet 9 was most likely to be found. Based on the orbital mechanics of the objects whose clustering had motivated the proposal, Brown and Batygin themselves began an ambitious observational search, combing through archival images and conducting new observations with powerful telescopes on Mauna Kea in Hawaii and other premier sites. Brown was direct about his conviction. He eventually described the existence of Planet 9 as something he was 90% confident about. For someone who had built a career on rigorous skepticism about exactly this kind of claim, that was a striking statement of belief. But years passed, and the planet was not found. Survey after survey came up empty. The Zwicky Transient Facility, the Dark Energy Survey, Pan-STARRS, instrument after instrument, scanned the predicted regions of the sky without finding anything that matched Planet 9's expected characteristics. Each non-detection tightened the constraints on where Planet 9 could be, ruling out portions of its predicted orbit, but none of the surveys were comprehensive enough to rule it out entirely. The planet remained, as Batygin himself put it, an echo inferred from its effects, never directly seen. And then, in 2025, someone went looking through old data, very old data, and found something. Part 5. What Planet 9 would actually be. Before we get to that discovery and its surprising complications, it's worth pausing to appreciate just what kind of world Planet 9 is predicted to be, if it exists. Because it would not be anything like the planets we know well. It would be something in between the familiar categories. A world that our solar system apparently failed to produce in the ordinary course of planet formation, but which is extraordinarily common around other stars. Surveys of exoplanets, planets orbiting other stars, have revealed that the most common type of planet in the galaxy appears to be what astronomers call super-Earths, worlds with masses between roughly 2 and 10 times that of Earth. Too large to be purely rocky like Mars or Venus, but too small to have accumulated the enormous hydrogen-helium envelopes that make Uranus and Neptune look the way they do. These super-Earths come in great variety. Some are dense, rocky worlds with thick atmospheres. Others are smaller versions of Neptune, with cores of rock and ice surrounded by significant amounts of gas. They appear to be one of the dominant outcomes of the planet formation process around sun-like stars, and yet our own solar system has none. We jump from Earth at 1 Earth mass directly to Uranus and Neptune at about 14 and 17 Earth masses, respectively, with nothing in between. Planet 9, with its predicted mass of 5 to 10 Earth masses, would fill exactly that gap. Batygin and Brown have speculated that the most natural interpretation is that Planet 9 is something like a scaled-down version of Uranus or Neptune, a world with a solid core of rock and ice surrounded by a substantial, though not enormous, atmosphere of hydrogen and helium. At its enormous distance from the Sun, it would be extraordinarily cold, with surface temperatures near absolute zero. It would have no liquid water, no weather in any conventional sense, no chemistry that would be remotely familiar. How did it get there? No planet-forming mechanism can easily produce a world of this size at 400 to 800 astronomical units. The outer reaches of the solar system simply don't have enough material to form such a body in place. The planet-building ingredients are too sparse, too cold, and too diffuse. The most widely favored origin story is that Planet 9 formed much closer to the Sun, in the region where Uranus and Neptune formed, somewhere between about 5 and 20 astronomical units. During the chaotic early period of the solar system, when Jupiter and Saturn were migrating and ejecting enormous amounts of material, a close gravitational encounter with one of the giant planets could have flung a partially formed planetary core outward onto an extremely elongated orbit that carried it far into the outer solar system. Most objects flung outward by Jupiter end up escaping the solar system entirely, becoming rogue planets, drifting freely through interstellar space. But a fraction of them get launched onto orbits just barely bound to the Sun. Orbits that are elongated and distant, but stable over billions of years. If Planet 9's early, extremely eccentric orbit was then gradually circularized by some additional mechanism, perhaps the gravity of other stars in the Sun's birth cluster, or the tidal effects of the surrounding nebular gas before it dissipated, the planet could have settled into something like the orbit that Batygin and Brown propose. There is actually good evidence from the study of other planetary systems that this kind of ejection is common. The exoplanet surveys that have found so many super-Earths have also found that many of these planets are in chaotic, tightly packed systems where close encounters and ejections are likely. Our solar system may look unusually sparse and orderly, partly because it did experience exactly these kinds of ejections during its formation, clearing out the middle of its planetary roster and leaving the gap between Earth and Uranus that Planet 9, if real, would fill. If Planet 9 exists and is eventually found, it would be the first new major planet discovered in the solar system since Neptune in 1846, a span of nearly 2 centuries. It would not be a new discovery in the sense of something stumbled upon casually, the way Herschel accidentally spotted Uranus while scanning the sky with his homemade telescope. It would instead be the confirmation of a mathematically predicted object, the fruit of years of painstaking inference from the motions of small distant worlds, a triumph of exactly the kind of indirect reasoning that found Neptune. Some recent refinements to the Planet 9 hypothesis have adjusted the expected mass somewhat. A 2025 study by Amir Siraj, Christopher Chiba, and Scott Tremaine, using a larger sample of 51 extreme trans-Neptunian objects and running 300 computer simulations, proposed new orbital characteristics. A semi-major axis of approximately 290 astronomical units with a margin of error of plus or minus 30, an eccentricity of roughly 0.29, and an inclination of about 6 degrees relative to the plane of the solar system. They estimated the mass at around 4.4 Earth masses, give or take about 1.1 Earth masses, somewhat smaller than the earlier estimates. This refinement is significant because it would put Planet 9 in a region of sky that falls within the early observing footprint of a new telescope that was just coming online as the search intensified. More on that telescope shortly. But the orbital refinements also created a certain irony, because even as the theoretical case for Planet 9 was being sharpened and improved, a separate team of astronomers was rummaging through decades-old satellite data and finding something that pointed, or seemed to point, in a completely different direction. Part 6. A candidate emerges from ancient data in a research group at the National Tsinghua University in Taiwan. A researcher named Terry Fan and his supervisor Ichi Goto began an unusual project. Rather than searching for Planet 9 using new telescopes, they decided to look backward through time into the archives of 2 infrared space observatories that had operated decades ago and whose data had never been fully analyzed, with the specific goal of finding a distant solar system body. The first archive was from IRAS, the Infrared Astronomical Satellite, a joint NASA, UK, and Netherlands mission that launched in January 1983. For nearly 11 months, until its coolant ran out, IRAS scanned the sky at infrared wavelengths, creating the first comprehensive all-sky survey at those frequencies. It detected hundreds of thousands of sources, stars, galaxies, clouds of interstellar dust, and its data has remained scientifically productive for decades, long after the satellite itself fell silent. Among the objects it detected were many things that infrared telescopes can see that optical telescopes cannot, including cold, distant objects that glow faintly in infrared light even when they emit almost no visible radiation. The second archive was from Akari, a Japanese infrared satellite operated by the Japan Aerospace Exploration Agency, which launched in 2006 and gathered data until 2011. Akari performed its own all-sky survey in infrared wavelengths, overlapping in coverage with IRAS, but at different wavelengths and with somewhat different sensitivities. The key insight behind Fan and Goto's approach was simple but elegant. Planet 9, if it exists, would be an extremely cold object, cold enough that its thermal emission would peak in the far infrared, not in visible light. And because of its enormous distance from the sun, it would move very slowly against the background of stars and galaxies. But it would move. Over a period of 23 years, which is the gap between the IRS and Akari surveys, Planet 9 would have shifted incrementally in its position, following its slow arc around the sun. An object at 700 astronomical units might move only tens of arc minutes in 23 years, a tiny apparent shift by the standards of inner solar system objects, but measurable if you know what to look for. Fan and Goto began by casting a wide net, searching the combined IRAS and Akari databases for sources that appeared in one dataset at a particular position but were absent from that same position in the other dataset, with a corresponding source appearing nearby in the second dataset at a distance consistent with Planet 9's expected motion. They were looking for a moving dot, a dot that shifted from one position in 1983 to another position roughly 47 arc minutes away in 2006, which is what a planet in the range of 500 to 700 astronomical units might do from an initial catalog of roughly 2 million potential objects in the combined databases. Their algorithm produced 13 pairs of sources that warranted closer examination. One by one, they checked these candidates by eye, looking at the actual images rather than just the catalog numbers. They rejected 12 of them for various reasons. Some turned out to be noise artifacts. Some were in crowded regions where confusion between different sources was likely. Some didn't have the right color or brightness characteristics. One candidate survived, just one. In the IRAS data from 1983, there was a faint infrared source at a particular position in the constellation. Eridanus, a large constellation in the southern sky that snakes from the celestial equator down toward the south, celestial pole. In the Akari data from approximately 2006, that source was not present at the same position, but there was a source nearby, about 47 arc minutes away, with similar brightness and color characteristics. The two sources matched what you would expect from a single cold object at a distance of around 700 astronomical units, moving at a rate consistent with a very long period orbit around the sun. Fan felt the electric clarity of a potential discovery, He described feeling very excited, not least because a previous attempt to compare IRAS and Akari data for Planet 9 candidates had found nothing at all, which had suggested that either the planet wasn't in a detectable configuration or that the search methodology wasn't sensitive enough. Finding a candidate where previous attempts had failed felt encouraging. The team wrote up their findings and posted them to the RxIve preprint server in April 2005, simultaneously submitting the paper to the Publications of the Astronomical Society of Australia, where it was accepted for publication. If this candidate was real, it would represent a genuinely transformative discovery based on the brightness of the infrared sources in both datasets. Fan estimated that the object would need to be more massive than Neptune to produce the signals they were seeing, somewhat larger than the super-Earth sizes that Batygin and Brown had predicted, but not implausibly so. It would be located approximately 700 astronomical units from the Sun, towards the far end of the predicted Planet 9 distance range. And its orbital period, based on that distance, would be somewhere between 10 and 20,000 years, close enough to predictions that it seemed too remarkable to dismiss. But science is not a business where remarkable things can remain unchallenged for long. Part 7. But something's off. When the news of Fan and Goto's candidate reached Mike Brown, the astronomer who had proposed Planet 9 in the first place, his reaction was not celebration. It was calculation. And what that calculation produced was deeply, significantly troubling. Brown took the two data points, the 1983 IRAS position and the approximate 2006 Akari position, and worked out what kind of orbit an object moving between them would need to have. The motion of any solar system object encodes information about its orbit. If you know where something was at one time and where it was at another time, you can, with some assumptions, constrain the family of possible orbits that connect those two positions. The more data points you have, the more precisely you can pin down the orbit. With just 2 points separated by 23 years, you can't determine a unique orbit, but you can rule out many possibilities. What Brown found was not reassuring. For an object to have moved from the IRAS position to the Akari position in the way the data suggested, it would need to be on an orbit tilted at an extreme angle, roughly 120 degrees relative to the plane of the solar system. A tilt of 120 degrees means the planet would be on a nearly retrograde orbit, circling the Sun in the opposite direction from all the other planets. Instead of orbiting in the same counterclockwise sense as Earth, Jupiter, and Neptune, as seen from above the solar system's north pole, a planet on this orbit would be moving clockwise. This is not just unusual, it is, for Planet 9 purposes, fatal. The Planet 9 hypothesis is built on a specific prediction. The planet is supposed to explain why a particular group of extreme trans-Neptunian objects have their orbits clustered in a specific orientation in three-dimensional space. The gravitational mechanism that produces this clustering depends critically on the geometry of Planet 9's own orbit. For Planet 9 to act as the shepherd that the hypothesis requires, its orbit needs to be tilted at only about 15 to 20 degrees relative to the plane of the solar system, inclined enough to explain some of the observed properties of high-inclination outer solar system objects, but not so extremely tilted that it would be orbiting in a completely different plane from everything else. A Planet 9 on a 120-degree inclination would not produce the clustering of Kuiper belt objects that motivated the entire hypothesis. Its gravitational influence at that extreme tilt would be oriented in entirely the wrong direction to act as the required shepherd. It would be producing gravitational effects on the outer solar system. Certainly, everything with mass produces gravitational effects. But those effects would not look like what astronomers actually observe. Brown was unambiguous in his assessment. Whether the candidate is real or not, it is, in his words, 100% not Planet 9. And there is an even stranger wrinkle. If the candidate object is real, and if Brown's calculation of its orbit is correct, then its existence would actually make it harder, not easier, to believe in the original Planet 9. The two planets, the candidate and the hypothetical Planet 9, could not coexist on stable orbits. Their paths through space would be mutually destabilizing over timescales of billions of years. Their gravitational interactions would pump each other into increasingly eccentric orbits until one or both were ejected from the solar system. If the Fan and Godot candidate is a real planet, then that planet would essentially disprove Brown's own prediction of Planet 9. Because they cannot both be there. Brown acknowledged this with what seemed like genuine scientific equanimity, describing it as kind of fun that a paper claiming to find Planet 9 had actually found something that would invalidate it. There is a kind of beautiful ruthlessness to the scientific method that this moment exemplifies. You propose a hypothesis. You define what would confirm it. And you also define, this is the part people often forget, what would disprove it. Brown had always been clear that his hypothesis was testable and could in principle be wrong. Finding a candidate that contradicts the prediction is not a failure of science. It is science working exactly as it should. The skepticism didn't stop with the orbital analysis. Other astronomers raised additional concerns. Astronomical observer Gary Bernstein pointed out that the candidate is just two data points, two tiny dots in archival images from different telescopes observed under different conditions, separated by 23 years. The history of astronomy is full of candidate detections that dissolved on closer examination. Two dots appearing in the right places at the right times with compatible colors and brightnesses is suggestive, but not remotely conclusive. They could be unrelated objects, an asteroid at some other distance, and an unrelated galaxy or infrared source that happened to match the expected signature by coincidence. With the enormous volume of data being searched, some false positives are statistically expected. The team itself acknowledged that follow-up observations are essential. Fans searched for the candidate in data from NASA's Wide Field Infrared Survey Explorer, another infrared satellite that surveyed the sky between 2009 and 2011. Roughly contemporaneous with the Akari observations, no clear counterpart was found in the WISE data, which is concerning. It could mean the object isn't there, or it could mean the object has moved enough that searching at the wrong position would miss it. Without better knowledge of the orbit, finding the object in a third data set is difficult. The University of Regina astronomer Samantha Lawler, one of the most persistent skeptics of the Planet 9 hypothesis in general, raised the foundational concern that has always shadowed the entire enterprise: the orbital clustering of extreme trans-Neptunian objects that motivates the Planet 9 prediction may not be a real physical effect at all. It may be an artifact of observational bias. Astronomers do not survey the sky uniformly. They observe in particular directions, at particular times of year, using particular instruments that have specific sensitivity limits. If the objects with the most extreme orbits have primarily been found in one region of sky, it might simply be because that's where people looked. The apparent clustering could be a product of the search process, not a genuine feature of the solar system. This possibility has been rigorously examined by Brown and Batygin, who have developed methods to quantify and correct for observational biases in their sample. After accounting for these effects, they maintain that the clustering remains statistically significant with a probability of occurring by chance of about 0.2%. But others, looking at the same data with different assumptions and different bias correction methods, arrive at less striking results. The debate is genuinely unresolved, and it has been going on for nearly a decade without reaching a clear conclusion on the basis of currently available data. The 2025 candidate, then, exists in this complicated landscape. It is tantalizing enough to generate real scientific excitement and international media attention. It is simultaneously uncertain enough that even its proposers cannot confirm what it represents, and it carries the additional paradox of potentially disproving the very hypothesis it seems to support. It is a characteristic moment in the search for Planet 9, a moment where everything feels simultaneously promising and entirely unclear. Part 8. The Stranger Possibilities. Alternative Explanations. The dissonance between the Fan and Goto candidates' apparent properties and the requirements of the Planet 9 hypothesis opens a door that has always been present in this story, but is now worth walking through more deliberately. What if the gravitational fingerprints that Batygin and Brown identified in the outer solar system are real, but the thing that left them is not a planet in any conventional sense? Two astronomers, Jakub Schultz from Durham University and James Unwin from the University of Illinois at Chicago, proposed in 2019 that the gravitational perturber in the outer solar system might not be a planet at all, but a primordial black hole. A primordial black hole is a hypothetical object formed not from the collapse of a star, but from the extreme density fluctuations of the very early universe, in the fraction of a second after the Big Bang. In the extraordinarily hot, dense, rapidly evolving conditions of those earliest moments, regions of matter that were slightly denser than their surroundings could have collapsed directly into black holes of a wide range of masses, some as small as subatomic particles, others as massive as stars. Most models of primordial black hole formation have been ruled out by cosmological observations, but a narrow window remains open for black holes in the mass range of a few Earth masses, objects that would be extraordinarily compact, perhaps the size of a bowling ball or a grapefruit, while containing several times. Such an object would be essentially invisible. It would emit no light. It would not interact with other matter except through gravity. It would generate no infrared glow that an all-sky survey could detect, and yet its gravity would exert precisely the same long-range influence on the outer solar system as a conventional planet of the same mass. Schultz and Unwin pointed out that the probability of the solar system having captured such a black hole during its history is not enormously different from the probability of having captured a rogue planet of similar mass, and the latter is itself one of the proposed origin stories for Planet 9, since planets get ejected from forming systems all the time. If there is a population of planet-mass primordial black holes drifting through the galaxy, which some models predict, but none have confirmed, the solar system could, with small but non-negligible probability, have gravitationally captured one at some point in its past. Konstantin Batygin himself acknowledged that while the primordial black hole idea is a stretch, it is not entirely implausible. The physicist Edward Witten, one of the most distinguished theoretical physicists alive, proposed a scheme to detect such an object, send a fleet of small spacecraft toward the predicted location, accelerated by light pressure from powerful lasers, and look for the gravitational lensing signal that a compact massive object would produce. The logistics are challenging, but the physics is sound in principle. A more practical approach was proposed by Amir Siraj and Avi Loeb from Harvard. They suggested that the Vera Rubin Observatory, with its combination of sensitivity and wide field of view, could potentially detect a primordial black hole in the outer solar system by looking for flares. Occasionally, icy objects from the Oort cloud pass close enough to any compact object that they get tidally disrupted and accreted, releasing a burst of radiation. Such flares would look different from the steady thermal glow that a conventional planet would emit, and detecting one would represent compelling evidence for a black hole rather than a planet. The absence of such flares over the course of the Rubin Observatory's planned decade-long survey would argue against a black hole and in favor of a conventional planet. There are also more conservative alternative explanations for the orbital clustering of extreme trans-Neptunian objects that don't require any new planet at all. One is a distant disk of small icy bodies, a ring or swarm of material extending through the outer solar system, whose collective gravity could, in principle, produce some of the gravitational effects attributed to Planet 9. Another is a self-gravitating instability in the outer Kuiper belt, a phenomenon that might spontaneously produce clustering over long timescales without any single dominant perturber. The observational evidence needed to distinguish between these possibilities is substantial, and it has been accumulating slowly. What the field needs is not more theoretical models. There are plenty of those. But more objects. More extreme trans-Neptunian objects detected by deeper surveys, measured with higher precision, and covering more of the sky more uniformly. With a large enough sample, statistically corrected for observational biases with high confidence, the question of whether the clustering is real becomes definitively answerable. And with a clear answer to that question, the search for an explanation can proceed on solid ground. As of early 2000-2006, that larger, more uniform sample doesn't quite exist yet. But it is coming, and the instrument that will deliver it has already had its first light. Part 9, The Reckoning. Vera C. Rubin Observatory, high on the ridge of Cerro Pachón, in northern Chile, in a region of the Atacama Desert known for having some of the clearest, driest skies on Earth. A new telescope has been awakening. The Vera C. Rubin Observatory, named after the pioneering American astronomer who provided crucial early evidence for the existence of dark matter, began commissioning in 2025 and released its stunning first images to the world on June 23, 2025, with full scientific operations beginning later that year. What makes Rubin extraordinary, even among extraordinary telescopes, is not any single attribute, but the combination of several attributes that individually would each be impressive. The telescope has an 8.4-meter primary mirror, already large, though not the largest in the world, but it couples that large aperture with an enormous field of view, 3.5 degrees across, which corresponds to an area of sky 9 times larger than the full moon. And at the focal plane of this wide-field telescope sits the largest digital camera ever built, the LSST camera, which contains 189 individual CCD sensors arranged in a mosaic, producing images at 3,200 megapixels, 3.2 gigapixels per exposure. The result of combining a large mirror, a wide field, and an enormous camera is a telescope with what astronomers call étendue, a measure of how efficiently a telescope collects light from a wide area of sky simultaneously. By étendue, Rubin is not just the best telescope in the world at its primary mission. It is an order of magnitude better than any previous instrument. Each image Rubin takes covers an area equivalent to about 45 full moons, and the telescope can image the entire southern sky visible from Chile roughly every 3, accumulating a complete, deep, multicolor survey of billions of objects at a pace that would have been unimaginable a generation ago. Over its planned 10-year legacy survey of space and time, which astronomers call by its acronym LSST, the same initials that also describe the survey camera, Rubin is expected to detect and catalog approximately 38 billion cosmic objects, including roughly 20 billion galaxies, 17 billion stars, and millions of solar system objects. It will process approximately 20 terabytes of data every single night, automatically identify anything in the sky that has changed, a star that has brightened, an asteroid that has moved, a galaxy that has developed a new point source, and issue up to 10 million alerts per night within 60 seconds of detecting a change. It will create, in effect, a 10-year movie of the changing sky, frame by frame, night by night, in unprecedented detail. For the Planet 9 hunt, specifically, Rubin offers capabilities that no previous instrument has matched in a single package. It will systematically survey the entire observable southern sky, including the regions where Planet 9 is most likely to reside, based on orbital predictions. It will be sensitive enough to detect objects far fainter than Planet 9 is expected to be, even at the most pessimistic end of its predicted distance range. And its ability to detect slow-moving objects by comparing images taken nights or weeks apart and measuring the tiny shifts in position that only solar system bodies exhibit is precisely what the search requires. Scott Shepard, one of the most experienced hunters of distant solar system objects, estimated a 70 to 80% probability that Rubin will find Planet 9 if it exists. Over the course of the survey, Batygin himself has expressed excitement about Rubin's potential, noting that even if the telescope doesn't directly spot Planet 9, it will find vastly more extreme trans-Neptunian objects, dramatically expanding the sample on which the statistical case for the planet's existence is built. If Planet 9 is there, Rubin's observations should either detect it directly or narrow its position to the point where targeted follow-up with other instruments can pin it down. And if Planet 9 is not there, that too is a scientifically valuable outcome. If Rubin's comprehensive, unbiased survey of the outer solar system fails to produce the orbital clustering that Batygin and Brown have predicted, and if it maps enough of the extreme trans-Neptunian object population to make confident statistical claims, then the Planet 9 hypothesis will be effectively falsified. The field will need to move on, find a different explanation for the existing apparent clustering, or conclude that the clustering isn't real. Either way, the uncertainty that has hung over this question for nearly a decade will begin to resolve. This is how science is supposed to work. Build the best theoretical model you can from the available evidence. Make testable predictions. Then build or commission the instruments needed to test those predictions. And accept whatever the data says. Rubin is the instrument that will, within the next few years, force a decision on one of the most captivating questions in planetary science. Part 10. What it would mean. Let us end tonight's journey not with uncertainty, which is the honest scientific position, but with possibility. because the possibility here is extraordinary in either direction, and it deserves to be contemplated fully. If Planet 9 is real, and if Rubin or some future instrument finds it, the implications ripple outward in ways that touch almost every field of planetary science. The most immediate implication would be for our understanding of solar system formation. The existence of a super-Earth or mini-Neptune in the outer solar system would confirm that planet formation in our solar system was more tumultuous and productive than the current planetary roster suggests. It would tell us that our Sun once nurtured a larger, richer family of worlds, and that the violent early history of the giant planets disrupted and scattered some of them to extreme orbits, or out of the system entirely. This is already suspected, but not confirmed. Detecting Planet 9 would provide the first direct evidence. It would also change how we think about the Kuiper Belt and the extended outer solar system. Planet 9's gravity has been shaping the outer solar system for billions of years, sculpting the orbits of hundreds or thousands of small bodies into the configurations we observe. Understanding that sculptural influence in detail would require us to reevaluate much of what we thought we knew about how those small bodies got where they are. Objects like Sedna, whose enigmatic orbits have puzzled astronomers since their discovery, would finally have a clear explanation. There would also be implications for cometary dynamics. Some models suggest that Planet 9 occasionally perturbs objects in the inner Oort cloud, sending them on trajectories that carry them through the inner solar system as long-period comets. If that's true, Planet 9 may have shaped the history of cometary bombardment on Earth, possibly influencing the delivery of water and organic molecules to the early Earth, or contributing to the impacts that punctuate the fossil record with mass extinction events. These are speculative connections, but they are physically plausible, and they hint that the hidden giant of the outer solar system may have played a role in Earth's own history. The discovery would also transform our understanding of where our solar system fits in the broader context of planetary systems throughout the galaxy. The most common type of planet around other stars, the super-Earth, is precisely what Planet 9 is predicted to be. Finding one in our own solar system, banished to an extreme orbit by the chaos of early planetary migration, would help us understand why these planets are so common elsewhere and why our solar system's planetary roster looks so different from most. It would make our solar system less of an anomaly and more of a typical outcome of a process that frequently produces super-Earths, but sometimes scatters them to the far edges of their systems. And then there is the deeper, quieter significance, the one that doesn't fit neatly into a scientific paper, but that anyone who has ever stared up at the night sky will understand instinctively. For all of human history, our solar system has had the same planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. 8 worlds, circling one star, the inventory complete and familiar. The idea that another world has been there all along, unknown to every human being who has ever lived, orbiting in the darkness beyond the familiar borders of what. There is something both unsettling and thrilling about that possibility. It would mean the solar system is stranger and more generous than we thought. It would mean the darkness is less empty than it appears. And if Planet 9 is not there, if Rubin surveys the sky for 10 years and finds no clustering, no candidate, no distant moving dot that matches the predictions, then we will have learned something equally important: that the apparent clustering of extreme trans-Neptunian objects was an artifact of how we looked, not a feature of what is really out there. And we will have to explain the orbit of Sedna, the orbit of 2012 VP113, the high inclination objects, all the orbital puzzles that seem to point toward Planet 9 in some other way. That will be harder. But science does not get to choose which truths are convenient. What we will not have to do, in either case, is stop looking. The outer solar system is vast, poorly mapped, and the Fan and Goto candidate, whatever it turns out to be, reminds us that there are objects in the extreme outer reaches of our solar system waiting to be cataloged, classified, and understood. Some of them may be members of familiar populations, Kuiper belt objects, scattered disk objects, inner Oort cloud objects, caught at unusual distances or on unusual orbits for reasons that the orbital dynamics of the known solar system can account for if we work hard enough. And some of them may be genuinely unexpected. Science has a long history of finding things it wasn't specifically looking for. And the outer solar system, so poorly explored compared to the inner planets, seems like a particularly fertile ground for such serendipity. There is a world out there, or there isn't. We're very close to finding out. Closing. It is a remarkable thing to exist at a moment when a question like this is approaching resolution. To live in an era when a telescope in the Chilean desert is systematically photographing the entire available sky every few nights, accumulating the data that will either confirm or deny the existence of a world that no human being has ever seen. To be alive when old data from satellites launched before some of you were born is being reanalyzed with fresh eyes and new algorithms and producing, perhaps, the first glimpse of a planet. To share a moment in time when the inventory of the solar system might finally be about to change. That's where I'd like to leave you tonight. Out there, in the cold darkness beyond Neptune, something is happening. Or it isn't. The mathematics are doing their patient, invisible work. The universe is keeping its secrets, but not for much longer. You don't need to understand every detail. You don't need to remember every number. What matters is that sense of wonder, that quiet awareness that the universe is enormously larger and more complex and more interesting than any single human mind can fully hold, and that the people who study it, who devote their careers to chasing faint dots of infrared light through decades of archival data, who run simulations for years to understand the gravitational influence of a planet that hasn't been found yet, who build telescopes on remote mountain ridges so they can see just a little further into the dark, are doing something genuinely extraordinary on behalf of all of us. Let that wonder be the last thing you carry with you as your body grows heavy and your breath grows slow. The universe is out there, vast and indifferent and beautiful, turning on its enormous cycles, keeping its own time. You are a small, warm, improbable miracle inside it, resting for a few hours in the dark. And somewhere far beyond the orbit of Neptune, in a cold that makes our winters feel like summer afternoons, something is making its long, slow arc around the sun. Maybe someday soon, we'll see it for the first time. Sleep well